All right, the next unit we're in is called sampling distributions. Now, this week, as we go through this, the key for you, number one most important priority you have, is to make sure that those two words in that order, sampling distribution, actually make sense to you. Mathematically, we'll go through what's expected of you in the following 2 weeks. And I'm going to show you some math this week. But ultimately, what's most important right now is you get what that's saying. The sampling distribution. Now, so far we've learned you've got something called a normal distribution. And let's say this normal distribution is representative of ACT scores from 2013. Hey, that's you. All in there. And then you'll have a mean, and let's say it was like, 20.5. And then there was a standard deviation, and it was like, let's call it 4. So then that means one standard deviation up would have been 24.5, and then two standard deviations out would have been 28.5. And in the other direction, one down would have been 16.5, and 12.5 over here, if that's at all possible. And then you had that distribution, and then somewhere on this chart, you'd find yourself, and I'm sure many of you would be way out here. But the key is that this is a distribution of everybody individually. This is the individual ACT scores as they're distributed. And then you would find probabilities within this. So let's say you want to know what's the probability of a randomly selected person that took the test in 2013 scoring a 26, which is somewhere in there or more. So then you'd find this area right here using normal CDF or looking it up on a chart, whatever floated your boat there. And that was simple enough. And you'd find that area using normal CDF, and it would help to get the z-score. And you'd take the z is, and I said 26, minus 24 or 20.5 over 4, and then you'd get whatever that value is, and then I guess it's 6.5 over 4, and then you would then find the probability of getting that z or more. Now what the sampling distribution does is it takes, instead of you dealing with these things individually, you now are going to start dealing with them in groups or in samples. Might be better said. Can't seem to get this little thing out of here. Let's make it shrink and go. So now instead of us looking at the ACT scores in the distribution, let's say this is it again, and the mean is 20.5. Now, I'm going to ask this. What if I take every single person that took that test, and then I start making SRS, simple random samples, of 25 from that population? And I keep doing it, and I keep doing it, and I keep doing it. I keep getting simple random samples. So in other words, if you can take a look at this, move that thing, take a look at that. I'm going to take a sample, and I'm going to get a mean from that sample. So I'll take my 25 students that took the test, and then there'll be some mean of all of their test scores. So that was like 21 or something. And then somebody else is going to take a sample from that population of 25, same number of people, and then they're going to get a mean. Let's say their mean was like 20. And then somebody else is going to take a sample from that population, and they're going to get a mean, and let's say their mean was like 21.2 or something. And on and on and on. Sample after sample after sample after sample after sample, and on and on and on. Hundreds upon hundreds of samples, thousands upon thousands of samples of 25. What's going to then happen with that group? What are they going to do when compared to this? And that's what a sampling distribution is, what I just said. When I take the sample after sample after sample after sample, and I get the mean of all those, and then I graph those values, what is that going to look like? That's the sampling distribution. Now, first and foremost from the sampling distribution is whatever the mean of the population is also going to be the mean of the sampling distribution. Because think about that for a second. I'm going to take a sample of 25 from a population whose mean is 20.5. And so is someone else, and so is someone else, and so are 2,000, 3,000 other people. They're all going to take SRSs of 25 people from that population. You would expect each and every time for the person that took their own respective sample to have a mean somewhat close to 20.5, not necessarily exactly 20.5, but around it, because that's what the actual mean was. And then maybe your mean of 25 people that took the test was like 22. You just happened to get a couple of 36s in yours. But somebody else's was 19, and a couple other people's were right on 20.5, and a couple others were 21, and a couple others were 20, and so on and so forth, and on and on and on. Eventually, when you start making the graph of all of those means of the 25, then the mean of that graph is going to be the same as the mean of the population. It has to be. There's no two ways about that. But there is going to be one slight difference in the look of the graph. As this was the distribution of everybody individually, what's going to happen when I put them in groups of 25? What is the graph going to then look like? Well, it's going to be a lot harder for me to get a sample of 25 to land way out here or way down here. Because for the most part, like we've already said, I'm going to be kind of near the mean. It's going to be a little bit more difficult to get way out here or way up here with my randomly chosen 25, because then I'd have to get a bunch of 34s and 35s and 36s to land out here. And I'd have to get a bunch of 11s, 12s, and 13s to land out here, when the fact of the matter is this is where the bunches are. They're all around here, and in fact 68% of them are going to be in between those two standard deviation lines. So, because of that, the graph of all of the 25s is going to look a little bit more like this. Where, and I'm sorry, it went out of screen there, I'm still at a mean of 20.5, but my variability has decreased dramatically. Now, I'm not going to be ranging way out here with my samples. They're going to be far, far less common to land way out there and way out there. My variability is going to be much tighter. The graph is going to squeeze in around my mean, which is, in this case, 20.5. Okay, now I said a key word there. I said variability. Now, what does that exactly mean? Well, you've got your normal distribution of everybody that took the test, and it varies about the mean as such. And by as such, what we're indicating is this standard deviation. So there's a value of the standard deviation, and then there's another standard deviation line here, and it's the same exact value there. And there's another standard deviation line here, and it's the same exact value there and there. That standard deviation is how it varies. Now, if you've noticed, with the second graph that I drew, that is of the sampling distribution, this one right here, now if I drew in the standard deviation lines, my first one would be right about there and right there. It'd be much tighter around that blue line. And my second one would be right there and right there. What has dramatically decreased? What has dramatically gone down? The variability. The standard deviation has gone way down, because instead of taking everybody individually, now I'm taking them in groups of 25. And so therefore, the variability has to decrease. Let's look at another example. Let's take this television show right here, Survivor. Survivor is a very popular television show on TV, and it's important for television executives and the such and the advertisers to know just how popular is the show, such that they are paying appropriately to run ads during the show, and in fact they're running ads period, because they know enough people are watching and the right people are watching. So then therefore they have to know how many people are indeed watching the show. Now the only way that can be done is by taking a sample. Now if we took a sample of, let's just go out and say 1,000 people, a random SRS of 1,000 people, and asked, what were you watching on television last night, if indeed you were watching television? And we found that 37% said Survivor. Does that mean 37% of the people that were watching TV last night were watching Survivor? No, that means 37% of my sample were watching Survivor. But my sample, I'm trying to say, can be extended to the population. Can it? Can I do that? Well, then therein lies the power of the sampling distribution. What I've drawn here is a normal distribution that represents every single possible sample of size 1,000 from the population of people that were watching TV that night that Survivor was on. And the proportion of those, or the mean, if you will, for now, the proportion of those that were watching Survivor. Now, if I do that over and over and over again, if I get 1,000 people in an SRS and 1,000 people in an SRS, then I'll continually and constantly get values. And the values will always, or not always, but eventually, you'll start seeing that as I get 1,000 after 1,000 after 1,000 after 1,000 after 1,000 after 1,000, 1,000 after 1,000 after 1,000, the values are going to start showing this normal distribution. They're going to fit this because this exists. This is what it is. And this number right here is the actual mean. Now, one thing you have to accept when you're dealing with sampling distributions is that this number exists. There is some true proportion of people that watched Survivor that night. It does exist. If you were Zeus and you could go ask every single person that watched TV, were they watching Survivor or not, then you would get the actual true number of this. Like, that's an actual real number. Now, what I've done is I've taken one of these. Now, I don't necessarily know which one I got, but I know I got one of these. And I also know that of these, by these I mean those little X's, those blue X's I drew, 68% of them are from here to here. And I also know of these, 95% of them are from there to there. So if I'm going to get just one of these blue X's, 19 out of 20 times I do it, I'm going to land in between these two lines right here. And that's where the power of the sampling distribution comes in. Because since I know that, it's safe to say, as long as I'm using an SRS, that the 37 that I got is going to be somewhere pretty close to the mean. It's going to be somewhere pretty close, somewhere in there, to the actual true proportion of people that watched Survivor that night. That's the power of the sampling distribution. So again, what we're trying to make sure here is that we understand what we're saying when we say this phrase right here, a sampling distribution. A lot of a lot of words go into this, and you got to make sure you know what these words are. For one, population. That's the total group of what you're looking at. All the people that watched television, all the M&Ms, all the students in the school, whatever it is. Now, remember when I used that Survivor example, I said that there was a normal distribution of that sampling distribution, and there was some true proportion of people that watched the show. That number right there is called a parameter, the number that describes the population. It always exists. If you wanted to know the true mean height of American adult women, you could take a sample to try to take a guess at it, but you do that knowing that there is an actual number. If you could possibly measure every single American adult woman in the United States and get their height, you could get the actual true mean height. That's the parameter, that number that we just said. And then there's a sample, and that's the small group from the population you choose in order to gather a statistic, which is the number that is produced from your sample. Again, I know I've said this before, notice the alliteration. The population is described by the parameter, the sample is described by the statistic. And then there's a couple other words we defined, or should define in this chapter. We already defined variability. So in other words, this graph that I've drawn over here has greater variability than this graph right here, because it ranges far further out. This graph has less variability. And then there's bias. Now with bias, the key with this one is that this phrase right here, unbiased estimator, is understood in that your sample is an unbiased estimator of the parameter. You didn't introduce any bias into what you did. You didn't cherry pick your sample. Unbiased estimator. And then, of course, there's the sampling distribution itself. And the sampling distribution, the definition of that is something that you should be able to spit out by yourself. You should be able to say the sampling distribution of a statistic describes the values of the statistic in all possible samples of the same size from the same population. And it is not the distribution of the population, it's the distribution of the samples of the same size from the same population. Again, the key this week for you is to make sure that this phrase, sampling distribution, makes sense to you. From here till the time you never see me again in May, we are going to be utilizing sampling distributions. And it's critical that the phrase itself makes sense, because if it doesn't, then as I start going through things like significance tests and confidence intervals, you're only going to be memorizing what I'm saying. It's not going to quite make sense because this never made sense. So it's critical this makes sense. I will say it 1,000 times if I have to, and I'll keep saying it over and over again to make sure we all get this. Sampling distribution of a statistic describes the values of the statistic in all possible samples of the same size from the same population.